Hello there and welcome back to this video series on control systems. In the last video, we have seen a brief introduction into the frequency domain, a kind of an idea as to how the frequency domain design goes. And we also defined several terms such as resonant peak, gain margin, phase margin, gain crossover, frequency, phase crossover, frequency, and so on. And we have also established the relationship between transient response specifications and frequency response specifications. That is, what is peak overshoot and how it is related to resonant peak, what is gain margin, phase margin, how they are related to the transient response specifications, how you can infer the values of the velocity error coefficient, velocity error constant, acceleration error constant, and position error constant, and overall design procedure is explained. It always helps to review the previous videos, that is 55 to 60, because we'll be building on these in the design process. After watching this video, a student will be able to specify the frequency characteristics of a lead compensator, what is the maximum lead that is given by a compensator, and how that can be computed and inserted into the design process. And perhaps we'll see the overall design process of a lead compensator. The transfer function of a lead compensator is given by k into s plus zc, 0 of compensator, s plus pole of the compensator. 0 of the compensator we take as 1 over t, pole of the compensator we take as 1 over alpha t with alpha less than 1. We will see why it is called lead compensator in a minute, but for now, notice that the geometric mean of the pole and 0. Pole is 1 over alpha t, 0 is 1 over t. If you take the geometric mean is the square root of the product. You see 1 over t times square root of alpha. We'll come back to it once again somewhere at some point in this video. A few important points about lead compensator are given here. Lead compensator introduces a dominant 0 and a pole to the transfer function. Thus, it improves the damping of the overall system. If there is a dominant 0, it improves damping. Okay. Less rise time and settling time, therefore transient response gets improved. Then the addition of lead network improves the phase margin and maximizes the velocity constant of the system. The pole 0 locations of lead compensator are given here. This 1 over minus 1 over t is the 0, minus 1 over alpha t is the pole. You can see that the 0 is closer to the imaginary axis. That is why we said it is dominant 0. And we have mentioned about it in the previous slide. And if you have to realize this lead compensator, a network something like this can be used. If you consider an input voltage and an output voltage with network components arranged as shown over here, this gives a lead action. You can derive the transfer function and see how it comes about. If you want to see the sinusoidal transfer function for this lead compensator, you substitute S is equal to j omega and you get something like this. We call it K1 G1 j omega, where K1 is alpha times K, where K is the open loop gain, alpha is a parameter of the lead network. And we use this notation G1 of j omega to indicate the dynamic part of the lead compensator. So we'll try to see how to compute these values of alpha and t, and then see how we can compute k1, followed by an example in the next video. The body plot here shows the characteristics of the lead compensator. If you see the phase curve, there is a frequency where the phase is maximum, and we denote this frequency by omega m. It is not quite visible, but it is omega subscript m. At omega is equal to omega m, the phase contribution of the lead network is maximum phi m. At all the other places it is less than the maximum. Also you see that the magnitude is virtually zero at all low frequencies, and reaches a maximum at high frequencies. So you may call it as a high pass filter. Note carefully that when omega is omega m, the phase is phi subscript m, and a corresponding magnitude m subscript m. As seen in the body plot, at low frequencies, the lead compensator does not add any gain or shape. So the low frequency portion is not affected. So if we use a lead compensator, the steady state gains that we achieved by whatever adjustment, they are not disturbed, because in low frequencies, the lead compensator does not add any gain or phase. But at high frequencies, the gain is increased, and there is a frequency where maximum phase angle is added. We have seen this in the previous body plot. Okay, because it adds phase angle, we call it a lead compensator. We'll try to find the frequency omega m where this maximum phase occurs, and find what is this phase phi m. We'll try to compute the frequency where maximum phase occurs and what is that maximum phase. We note that the compensator is given by this sinusoidal transfer function, and thus the phase of this is angle of g1 j omega, which is angle of this minus angle of the denominator, angle of the numerator minus angle of the denominator. Thus we see that phi c is tan inverse omega t, tan inverse b by a, tan inverse b by a, tan inverse alpha omega t by 1. Thus we see that for maximum phase, the derivative of this with respect to omega must be 0. So this is 0, and thus we have omega is equal to omega m is equal to 1 over t root alpha. If you solve this equation, you will get omega is 1 over t root alpha, which is the mean of geometric mean of the zero and pole, as we have noted in previous slide. Remember this value of omega m, which is 1 over t square root alpha. To compute the maximum phase, we substitute the value of omega in equation into equation 1. We get the maximum value of phase as given here. So phi m is all this, and phi m, if you simplify all this, you'll get 1 minus alpha by 2 square root of alpha. If you use this trigonometric identity, you get it into a convenient form, sine inverse 1 minus alpha over 1 plus alpha s. You need to remember this equation. Phi m is sine inverse 1 minus alpha by 1 plus alpha. That is, choosing an alpha, we can achieve a lead angle, maximum lead that you can add to the system. Uh, Sine phi m is 1 minus alpha by 1 plus alpha. So alpha is 1 minus sine phi m by 1 plus sine phi m. This equation 3 you need to remember carefully. Thus, to initiate the required information for the design, we see that equation 3 is very important equation. Given the phase lead, we can find the value of alpha using equation 3. Substituting the value of alpha from equation 3 and the value of omega m from equation 2 into the sinusoidal transfer function, we see that the gain contribution, that is 20 log to the base 10 magnitude of g1 j omega as 20 log to the base 10 1 over square root of alpha. Remember this equation 4 very carefully. We'll come back to it at some point of time. Having seen all those equations which are necessary for computing what is the maximum phase angle that a lead network can add, and also what is the uh, gain at the frequency where maximum lead angle is given. Given all these, we can lay down the design procedure as shown here. From design specifications, find the value of gain K1, that is the constant value is computed first, and then from the body plot, find gain, crossover frequency, and phase margin. Phase margin is gamma. If the specified value is gamma specified, find the phase lead that the network needs to add, that is gamma spec minus gamma. From this, we find alpha using the equation 3. That is, you'll first find out what is the gain margin of the existing system, and then you find what is the phase margin that you need, the difference between the phase margin needed minus phase margin existing, that is gamma specified minus gamma. You find what is the phase lead. Once you know the phase lead, we can find alpha. Once you have alpha, you can use t is equal to 1 over omega m square root alpha. Then you draw the body plot of the design system with the compensator. If all the design specifications are met, obviously our task is done. Otherwise, we'll kind of try to tweak the values of omega m, t, and alpha. This procedure is explained with an example. In summary, we see that the lead compensator is used to increase the phase margin. We have computed what is the maximum phase that a lead compensator can offer. And we saw that in a nutshell, the design procedure is to find the value of K1 to satisfy the steady state requirements, then compute the dynamic part to satisfy other requirement. We see that the lead compensator is a high pass filter. High pass filter. I think that's all we have for now. Have a great day.